So finally, in this set of videos on screening and diagnostic testing in epidemiology, I want to discuss some potential biases that we have to consider when evaluating the effect or use of a screening program at a public health level. The three I want to discuss are listed here: the lead time, length, and volunteer bias. The first lead time bias is a bias that occurs when screening detects disease earlier in its course, for example, during the latent period, than if the screening had not been performed at all. That is, the disease was identified via a clinical presentation of clinical signs and symptoms by the patient, led the patient to seek clinical care, and at that point their disease was diagnosed. What happens is that this lead time biases the comparisons if those comparisons are not adjusted for the timing of the diagnosis. And that's because the length of time from the point of diagnosis via the screening approach to the time of death is increased, but not necessarily the length of life, particularly if the treatment is ineffective or the patient dies from something else. So this is an issue that occurs in several types of cancer screenings. And there's one approach that can be used to avoid it or reduce it, and that's by measuring the overall mortality associated with the disease and not the survival. And I want to go into an example of why that is and what is the difference. But before I go into that, I want to provide an example of lead time bias in a very simplistic diagram shown here. So up top I have the scenario of an individual who doesn't have early detection, for whom we don't screen. So their cancer begins at age 40, and they're diagnosed with the cancer at age 44 because they come in with clinical signs and symptoms. And they die at age 50, so they have 6 years of living from the point of being diagnosed to the point that they die. In the bottom half of this slide, I'm illustrating a scenario where there is screening for that cancer, such that the disease still starts at age 40, but they're screened at 2 years from the beginning of the onset of the cancer. So they're screened at age 42, and it's at this point that they don't have clinical signs and symptoms because this is via screening approach. And so then they live for 8 years because they still die at age 50 like the person up here. It appears that they live longer after diagnosis, but they die the same length of time after the onset of disease. So this is an example of the lead time bias in comparing the results between, say, this individual and this individual. And now this is the slide or the example I want to provide in terms of whether to present mortality or survival. And this comes from a published example from the Mayo Clinic on a particular lung study. This was a randomized clinical trial to compare chest X-ray plus cytology versus the standard of care at the time for lung cancer screening. And in this paper and this study, they present the results of providing the 5-year survival between the two treatment arms, or the two screening arms. And the survival curve is shown up top here. This is called a Kaplan-Meier survival, where you have the probability of surviving on the y-axis going from 100% to 0, and time on the x-axis, such that we interpret this as time goes on, the probability of surviving decreases. And the curve with the faster drop is the one that's usually viewed as the one that has the less survival, or the survival time is shorter. So in this example, the usual care survival curve is faster than that for this new group, this screened group. And this figure essentially suggests that the new screening approach of chest X-ray plus cytology increases survival versus the standard of care. However, if you look at the same data, but now you're plotting the data as a cumulative plot, cumulative events, cumulative cancer death, because that is the ultimate outcome that we're measuring up here as well, survival. You now see that as you plot cumulative death as a function of time, you see that there really isn't as much of a difference between the two treatment groups, or the two screening groups, I should say. And this is a clear example of how if we present the effect of screening by looking at survival times, it could lead to a false conclusion. So now I talk about length bias. This is slightly different than lead time bias. This is a bias that occurs as a function of the severity of the disease. So as we've discussed, prevalence is a measure of the product of incidence and the duration of the disease. And as we know, by screening, we're picking up prevalent disease, right? We're not picking up incident disease. We're picking up prevalent disease. So the diseases that have a slower progression will have a longer duration in their pre-symptomatic stage, therefore a larger prevalence of that disease as well. And people with the less aggressive form of the disease will survive longer. That should be somewhat obvious. The longer it takes for your disease to evolve, the longer you'll live. So what happens is that people with the less aggressive form of the disease are often overrepresented among cases identified during a particular screening program, because the probability that the disease will be detected by the screening approach is directly proportional to the length of that disease's detectable preclinical phase, which is almost always inversely related to the rate of the progression of that disease. So people with less aggressive disease will survive longer after screening than those who have a more aggressive form. And now finally, I want to discuss volunteer bias. And this is a bias that occurs when people choose to participate in screening for one reason or another, and they're different from people who choose not to participate in screening. Oftentimes, people who are healthier or more health conscious are more likely to undergo a screening test than those who are not. And there are multiple ways to prevent or reduce volunteer bias. One would be to evaluate the effect of a screening using it in a randomized clinical trial, which will be discussed in a bit, but that is where we essentially randomly assign people to if they're going to get screening or not. So there isn't a bias at that point in terms of what the person receives in terms of the screening. However, you can still have a bias in a randomized trial in terms of who agrees to participate in the trial, and that really is something that can't be avoided at all. So other approaches to control for the volunteer bias can involve analytical approaches, by including information about the person who participates in the screening on their history of their disease, their level of health concern, and other health-related behaviors that we can include in models to essentially what's called control for those factors. And there are many examples in the literature about volunteer bias. There have been examples in a colon cancer screening study where the more healthy individuals chose to participate compared to those who were less healthy, and thus it led to an underestimate of the disease prevalence. There was another example of a physician's health study leading to substantially lower than expected mortality compared to the overall population. Again, with the idea that the persons who chose to participate in that study were a bit healthier than the overall population for whom the screening would be intended. So these are just the three key types of bias that we think about when we discuss screening and diagnostic testing.